Welcome to a Rice University digital media production. For more information about us, please visit our website at www.rice.edu.
Welcome to the Scientia Centennial Lecture Series. The 2011-2012 theme is Rice, a Century of Change. My name is Devika Subramanian. I'm a faculty member in the Computer Science Department, and I'm also a member of the Scientia board. In this centennial series, we look at Rice, a Century of Change. We look at the decisive events that have shaped this university since in its first century, and we explore the emerging fields of research that will shape the future of Rice. Today's topic is carbon nanotechnology at Rice, past, present, and future. To introduce the exciting events, 2 presentations and a panel, is my colleague, Professor Kevin Kelly from the Electrical and Computer Engineering Department. So Kevin, oh, there you are. Dr. Kelly earned his undergraduate degree in engineering physics from the Colorado School of Mines and his graduate degrees in applied physics from right here at Rice with Naomi Hallis. He served as a postdoc in Japan as well as at Penn State, and now he's one of us since 2002. So please help me welcome Kevin. He will do the introductions.
Welcome to this lecture in the Scientia series. I have to say that I'm really giddy with excitement in the sense that I had marked this one on the calendar as soon as the lecture series came out and did not imagine I was going to be taking Rich Baraniuk's place as the moderator. Unfortunately, he couldn't make it. But as was mentioned, I was a graduate student here at Rice, and it was particularly exciting at that time because there was a lot going on in carbon nanotechnology in particular, and there was a lot of buzz about when the Nobel Prize would be awarded or if it would be awarded, and I had the privilege of being a graduate student when that happened. I also had the privilege of having worked with and currently work with everybody on the panel, and I just wanted to say that I think we'll have a very lively discussion. I'm going to first start off by introducing the first 2 speakers. They're going to give an 18-minute lecture apiece, and then after that, I'll introduce the next 2 panel members, and we'll get them all up here, and I think we'll have a lively discussion. Our first speaker is Professor James Tour. He is Professor of Chemistry, Computer Science, and Material Science. I had the privilege of actually studying his single molecule switches and wires while I was a postdoc at Penn State. And when I came to Rice, we began to talk about some of the things I might do as a professor in collaboration with him. And as you'll hear about, one of the things we got to collaborate on, which was a very fruitful collaboration, was myself and my graduate students were the first nanoscale crash test dummies for the nanocar. So. As you will see, he is an amazing researcher. He has sort of a vision and imagination, inspiration that's only rivaled by his chemical synthetic capabilities. You will see wondrous structures, I think, that 20, 30 years ago people would have only dreamt of in science fiction. And also, not only is he very interested in research, he's very interested in education, and so I have to mention this because I've worked on a couple of NSF-funded grants with him. And he has created a lot of stuff for K through 12 outreach, including the nanokids, sort of organically inspired molecules in the shapes of familiar objects for children. He has taken some of our work and turned it into video games, including Dance Dance Revolution and Guitar Hero. So I think you'll get a very good lecture, and you'll see that imagination come out in his talk. The second speaker following him is Cyrus Mody. I had the great pleasure of meeting Cyrus when he was teaching the Nanotechnology Content and Context course here at Rice, and I was a guest lecturer in that course. And one of the things about him that struck me is that he had an incredible grasp of engineering and science, and lo and behold, he has a bachelor's degree in mechanical engineering before he went off and got his PhD in history. So he is professor of history at Rice, but he straddles a couple of fields between engineering, I think. He qualifies in my book as an engineer, science, history, and anthropology. And out of the Nanotechnology Content and Context course, and I think some of the ideas that will be discussed today include the impacts of nanotechnology basically on our everyday lives as people and as a society, And basically the challenges you have to tackle with that. And from our discussions in that nano class, we actually created a technology disasters course that was co-listed in the School of Engineering and the School of Humanities. And so I've had the pleasure of teaching alongside of him in that respect. And one thing I can say about both speakers is that every time I hear them speak, not only do I enjoy their lectures, but I learn something new. And so I think you guys will feel the same way. So first off, let's have Professor Jim Tour.
Thank you. So today I'm going to give you an overview of some of the work that we've done, and much of this is in collaboration with others here at Rice or in the Texas Medical Center. And the entire presentation is one slide, so this is not going to go away. This is just to help me with my talking points. We started, when we came here to Rice, when our group moved here to Rice 12 years ago, working with carbon nanotubes. And we had the good pleasure of having an abundance of carbon nanotubes relative to what many people could get their hands on. And we found that we could take carbon nanotubes and mix them with materials and really impact the toughness, the energy needed to break these materials. And we found that if we take carbon nanotubes and put groups on them, functionalize them, we could put them in host materials, and we would increase the energy needed to break those materials by quite a lot. And that's moved now into the oil industry, and these are blowout. This is what a blowout preventer looks like. You may have heard of those on the Horizon disaster. That didn't have carbon nanotubes in it. But now there are ones coming out with carbon nanotubes in them, and that's in a company called Nanocomposites, which is just now in the Woodlands, and it's owned about 50% now by Schlumberger, and moving rubber materials into the market. We've also taken carbon nanotubes and put them in composites and used these to heat up materials. We had noticed, I had a conversation once with Rick Smalley. I said, do carbon nanotubes absorb microwaves? He said they're the best microwave absorbers known. So I told the student to take a watch glass of microwaves and stick it in the microwave oven and come back and tell me what happened. He came back and told me that the oven exploded. I said, well, these are great absorbers. And so I called Rick. I said, they're really great absorbers. He said, why did you try that? I said, well, you told me they were good absorbers. I wanted to see how good microwave absorbers they really were. He said, I never told you that. I said, no, you told me that. That's why I tried it. He said he didn't even remember telling me that. He must have told me that just to get rid of me. But it turned out that we put this in with a composite material because I had asked NASA how they cure the composite materials if they have a defect in one of the edges of the space shuttle. He says, well, they use a NOAX. This is a pre-ceramic polymer. I said, but you have to heat that up to 1,000 degrees to get it to cure. They said, yes, we know that. We hope that it would cure upon reentry. So I said, that's a hard thing. And so we found out that we could mix carbon nanotubes with this NOAX material, and we could heat it up to 1,000 degrees in 300 seconds just using 30 watts of microwave. A typical kitchen microwave is 1,200 watts. So we built a little microwave apparatus with some of the folks in the CNL and showed that. And then we actually did it on space shuttle tiles, and they said they couldn't give it to us because those were proprietary materials, and we found a whole box of them in the machine shop. And when they came, they asked us where we got the space shuttle tiles. I told them, don't ask, don't tell. And so this is what it would look like. And so NASA has built a microwave gun, and actually that's not the microwave gun. That's actually a water gun that's been photoshopped in. Just to make it look, they won't show me what the microwave gun looks like because that's proprietary. A lot of work that's done here at Rice is with carbon nanotubes and to make fibers out of carbon nanotubes. And that work was started with Matteo Pasquale and Rick Smalley back in about 2002, 2001. So in about that time frame. And more recently, Professors Ajayan and Rick Barrera have spun some carbon nanotube fibers as well. This is a fiber made out of graphene oxide. So we're actually able to take graphene, which is a two-dimensional material, rather than a one-dimensional. So carbon nanotube is this one-dimensional material. Graphene is a two-dimensional material. We can just take bulk graphite, and we've developed a method now to oxidize bulk graphite to turn it into graphene oxide. And all of that technology has now recently been licensed. And we found that we could spin fibers out of those. And then another thing that we did is we found that we could take carbon nanotubes, multi-walled nanotubes in particular, and we could treat that in two different methods. One is with potassium permanganate and sulfuric acid, and that's a procedure that was developed, that's a mixture that was developed and used in the 1800s. And also just potassium metal. We could just mix it with the nanotubes and heat it up to 250 degrees, and that would split the carbon nanotubes, and they split longitudinally, just like if you have a pipe in your home and the pipe freezes, the water freezes in the pipe splits, never horizontally, but always longitudinally. And that's how these ribbons then form. So the carbon nanotubes, concentric rings, but then they'll split into ribbons, and then you're left with potassium atoms on the edges. So you have the aryl anions, and we could add vinyl monomers and polymerize off the edges. And we can use these structures. So this is actually what the ribbons look like. And so we can make large flasks of these. And again, this technology has recently been licensed. And we can take these ribbon structures and we can actually take Kevlar fibers. Kevlar fibers are just commodity materials now. They're put in rubber tires, for example. We could take Kevlar fibers. We can just coat them now with either nanotubes or nanoribbons, and we can light LED lights with them. And so one could think of making conductive clothing. So it'd be nice to have, walk in and just have the whole shirt glowing. But it's also good for electronic clothing if one wanted heating. So in other words, you can actually spin with these fibers now, and we figured out a method to be able to coat these so that they're electronically conductive, but they also will allow you to spin them and to knot them, which you can't do with a carbon fiber. We more recently found a method where we could take graphene and grow graphene. This is sheets of carbon 2D material. Others had found that you could take copper and hit it with methane at 1,000 degrees and grow sheets of graphene. And what we found is we could just take polymethyl methacrylate, which is an inexpensive polymer, put it on there and heat it to 1,000 degrees and get very nice graphene. So we were contacted by Mitsubishi Rayon because they make PMMA, the polymer, and they thought this would be a great markup for them. Then we found we could do it with sugar. And then we got contacted by the sugar companies because they thought that this would be a great markup for them. Then we found we could do it with roaches. This is a roach leg. So the exterminator comes to the house every 3 months, and after the exterminator leaves, I usually the next day find a roach jiggling around. And so I brought that roach in and told the student to put this on a piece of copper and heat it up to 1,000 degrees. We'll probably get graphene, and we did. And actually all the impurities stay on the top, and very clean graphene forms on the bottom. So you can make graphene now from any carbon source because carbon is carbon. Just the rearrangement of it makes a structural difference. And so one of the demonstrations that we recently did, which is actually on YouTube now, is we took a box of Girl Scout cookies, the shortbread kind, and there's 255 grams of carbon in that box of cookies, and it's $3.50, and we converted some of the cookies into graphene. And if you sell the graphene at the going price of about $200 per square inch of what they sell it for, you could make $15 billion worth of graphene from a box of Girl Scout cookies. So if there's any students here who feel entrepreneurial, this is be a good business to be in. We found that we could take these nanoribbons, which can be made in bulk now, and one of the things that we can do is we can coat these nanoribbons on surfaces and use these to heat surfaces. So my postdoc, Yu Zhu, was presenting this to Lockheed. We have a big program here thanks to Wade Adams for starting the Lockheed Martin program and the Lancer program with Lockheed Martin, and he was presenting this, and they said they had a number of calculations which showed that if you could have a conductive surface that's less than 100 nanometers thick, it would not obscure the radar waves that go through it. So these big white domes that you see at airports are radomes. These are the coverings for radars. And those are made out of aluminum oxide. And so it takes a lot of thermal energy to heat those, to de-ice them. But you need something like that to protect the radar surface. But they could get to a very thin structure if they could use something that's conductive but very thin. And so they learned about graphene. We told them about ribbons, and they said, could you take these graphene ribbons and make a coating out of them? And so that was the idea. Could we make a coating out of them and do de-icing? So what you see here is a piece of polyimide that's been coated with the graphene ribbons, and then with Carter Cottrell and with Abdul Rahman Raji and Yu Zhu, they put this piece of dry ice and sprayed Windex on it until they got 5 grams of ice coating it. And this is now held at a 45-degree angle in a box that's at minus 20 degrees by putting dry ice in the box and blowing a fan across it. This is just a thermocouple over the top to measure the temperature. And now we're putting 2.5 watts per square inch across that film, and the ice melts. And this is at minus 20 degrees, the ice melts. So now we're going up, and they've done all the radar testing on this to show that they don't absorb the radar waves. And now we're going up to a 1 square foot panel, and after that it'll hopefully be commercialized. This is for the Aegis cruiser, the big radar ships that are used by the US government. That would be the first application for those. And interestingly, when we first made these, they said it works great, but it comes off on our finger if we touch it. I said, well, don't touch it. It's only 100 atoms thick. You know, each one of these is an atom thick layer. It's only 100 angstroms thick, the entire film, but it's 1 atom thick layers. They said, oh no, this has to be mechanically robust. So we went down to O'Reilly's Auto Parts store in the Village and bought a can of polyurethane paint. This is just paint, but without the pigment or the dye. Very hard to optimize above car paint. It sits out in the blazing sun for 20 years, and it performs quite well. So then we just spray coated this on the surface. So Yuzu then put it on a hot plate at 200 degrees, gets it a little bit tacky, and then sprays the nano ribbons right into that. And now you get a very robust coating of nano ribbons. Another application is to take graphene oxide and use it in drilling fluids. This has now been licensed by MI Swaco, a drilling fluids company here in town, which is owned by Schlumberger. And this is to take the graphene ribbons, and we can take these and put these in solution with the drilling fluids. And the idea is if we make graphene ribbons, you see they plug every filter that you ever try to use. So we thought we could plug holes with this. So they put this in the drilling fluid, and the idea is that as they come down with the pressure here, high pressure, the drilling fluid won't infiltrate the pristine formation of the rock, because generally it does. Then they have to go through washing procedures to get that material back out of the rock before they can start yielding oil to come in. So under the higher pressure, these form a filter cake on the sidewalls. And then when the pressure is released, the oil just pushes this out from the other side. So a very simple application for bulk graphene oxide. Nice carbon material. We've also been able to recently take some of this graphene material and use it as a transparent electrode. So we've done a lot of demonstrations with transparent electrodes. You're familiar with transparent electrodes from your touch screen displays, and that's indium tin oxide on glass. The price of that has gone up 8-fold in the last 5 years because of the desire for photovoltaics, the large solar panels that are made. So it's hard producing that in bulk, and we found that we could make not just touchscreen displays, we can have embedded memory inside of flexible plastic. So one could think of then rolling up a cell phone, for example. This is the work on nanomedicine. This in particular, we take these carbon nanoparticles, which are really interesting structures, to take these carbon nanoparticles, and what we can do is we sequester a drug. So we first make the carbon nanoparticles water soluble by oxidizing the outside and attaching polyethylene glycol groups to the edges. And then we sequester a drug just by shaking it up with paclitaxel. You may have heard of Taxol, which is a frontline chemotherapy agent. We take paclitaxel, just shake it up. That's the active ingredient in Taxol, is paclitaxel. And it's sequestered by the carbon nanoparticle. And then we shake it up with a monoclonal antibody, and that's also sequestered by the nanoparticle, but it still remains active. It projects out its active site. And then we direct that to specific tumors. This is work with Jeff Meyer's group at MD Anderson Cancer Center. And so this is actually the flank of a mouse, and the mouse has had 2 tumors injected into it, one on the left flank, one on the right flank. And then the drug is injected into the tail vein, and it has to find the tumors. The right tumor is not targeted. The left tumor is targeted. And so you can see the left tumor is gone, the right tumor continues to grow. So you can see the effect of a targeted drug delivery versus an untargeted drug delivery. Taxol, the commercial formulation, is untargeted. This is exactly what the remains of what happens with Taxol in an untargeted delivery. This is what happens with a targeted delivery. And then in talking with Jennifer West, I could never really get her impressed with our nanomedicine work. And I said, why aren't you impressed? She says, oh, well, there's so many drug delivery agents out there. So could we find something where the nanometer-sized particle has an effect that no other material has? So in other words, that a small molecule can't do and that a protein wouldn't do. Can we have some activity? And so we started working with Baylor College of Medicine, Tom Kent's group, Tom Kent's group and Robia Potler's group at Baylor College of Medicine, we had seen activity in our carbon nanoparticles as great antioxidants. Now, this is a project that's funded by the Department of Defense for traumatic brain injury because so many of our soldiers are coming back from the Middle East conflict with head injuries from IEDs. And so the idea is that when there's an explosion and there's a head injury, that's a traumatic brain injury. But when that traumatic brain injury is associated with hemorrhagic shock, so in other words, a severed artery, loss of blood, often happens in a car accident as well. When there's a brain injury and loss of blood, the brain injury is exacerbated. And you can see this. These are pictures of a rat brain. Actually, my laser pointer just died out. Well, these are pictures of a rat brain. And you can see that this is a rat brain in which there's been traumatic brain injury. And so the brain is exposed. A steel ball is dropped from a certain height onto the brain. And you can see a small indentation on the brain that had resulted as a result of that injury. So this is on an anesthetized rat, and then eventually they'll take the brain out and examine it. If you have a brain, if you take a brain of a rat and just do hemorrhagic shock for 60 minutes, of course there's no contusion on the brain. But if you do the same blow to the brain and associate that with 60 minutes of low blood pressure, you can see this large contusion on the brain that stays forever with this rat. And so the motor task skills track with that as well. And so what we found, though, is we can inject these nanoparticles which will sequester the superoxide, which is the problem. This is why this damage occurs. We're now moving this into stroke models because it's a very similar model in stroke. And we can keep this contusion from happening. And we have direct results that show that in these formulations, when the superoxide normally goes way up, it's this superoxide, this release of these radicals in the brain upon reinfusion of blood, that what will happen is you get this big spike of superoxide, and we can bring that right back down to a normal level. We can bring that right back down with this drug. So in other words, here's something that a small molecule can't do. There are no drugs on the market to do this. 2 have entered clinical trials but have never come out of clinical trials. And so the hope is that now we can move this and begin to get this translated. And finally, I want to wrap up talking about our work on nanocars. Nanocars are these single molecule vehicles, and here's a picture of a nanocar. It actually has an embedded motor. This is 2 nanometers by 3 nanometers, so that you get an appreciation for how small these things are. These wheels here are about 3 water molecules across in size. So here's a fullerene wheel structure. This is the one that's shown here in the images. These images were taken by Kevin Kelly. And just to give you an idea of how small this is, again, 3 water molecules across for one of those wheels. If you have 500 sheets of paper, 500 sheets of paper is about 2.5 inches high. If instead of having 500 sheets of paper, you had 6 times 10 to the 23rd sheets of paper, which is the number of molecules of water that you would have in one swallow of water. So if you take a swallow of water, that's about 18 milliliters. That's 6 times 10 to the 23rd molecules of water, 1 mole of water. If you had 1 mole of paper, 6 times 10 to the 23rd sheets of paper, that stack of paper would be more than 2.5 inches high. It would reach from the Earth to the Sun 400 million times. So you'd have 400 million stacks of paper from the Earth to the Sun if you had a mole of paper. And so that shows you how small these really are. And what you can see is that Kevin's got these great pictures of these cars moving right across the surface. So here's a picture of a nanocar. It turns, and it starts to follow this tracked line across the surface. And there was the first nano collision ever recorded. Now, why would somebody want to do this? The idea is if we can learn how to move vehicles on a surface, could we eventually pick things up and move them and do bottom-up construction, much like enzymes assemble us today? That's nature's nanomachines which do the assembly. We have no way of doing that. When we want to build something, we build a podium, we find a big tree, we cut it down, we build a podium. That tree was made from the bottom up using nature's nanomachines, which are enzymes which do that construction. So to have that sort of assembly, that's what we want to move into. The wheels on our first nanocars were these C60 molecules that were discovered here at Rice. So that gives you an overview of some of the nanotechnology that's going on here at Rice. Thank you.
Thank you, Jim. And so now that we've heard about sort of the current and even had a peek at the future of what carbon nanotechnology might bring, as a researcher myself, I would also like to hear about how these great researchers started their labs. And we're going to hear now from Cyrus Mody and some lessons that we can all take away from the way Rick Smalley got into this game and sort of pulled all of us along on his coattails. So thanks, Cyrus.
Yeah. Thanks, Kevin.
All right, so the charge I've given myself today is to sort of step through the life and career of Rick Smalley and also the history of the discovery of carbon-60 and then the later emergence of a buckyball research community and the way that in turn impacted rice, but at the same time to also try and draw some lessons from that story for how science should be organized and how those of us in higher education can help foster healthy scientific research communities. Now, I'm going to draw 8 lessons. I think you could draw a whole bunch more. This is by no means a comprehensive list, and I'd definitely be interested to hear further lessons that people in the audience want to draw. There's a danger in a talk like this that centers so much on an individual of veering into hagiography, of this sort of glowing celebration of an individual's life. And certainly in Rice's 100th year, we should give ourselves the chance to celebrate the life of someone who was a driving force here for 3 decades. But I also recognize that Rick Smalley was a very complicated guy, and not everyone got along with him, and even some people who did felt very conflicted about him. Again, I'd be interested to hear from the audience other kinds of lessons we could take from his life and career. I will say, as an historian of science, one of the kind of appealing things about Rick Smalley is that he definitely was a very human character with all of the strengths and weaknesses that implies. He was no disembodied brain. He was a great brain, obviously, but he was also a very human guy who plunged into things and brought people together through the force of his personality. All right, so the first lesson. Some people need second chances. Some people take a while to get started in life. And this is a theme you see quite a bit in the history of science. Maybe the most famous example is Einstein. The one I often present to students in my history of science survey course is that of Darwin, who as a young man in his 20s seemed not to be a particularly promising character, maybe destined for life as a rather mediocre Anglican country priest with much more successful side hobbies as an investor and a beetle collector, but who took this voyage around the world on the HMS Beagle and really turned his life around and became the scientist that we know. And to some extent, Rick Smalley seems to have been a similar kind of character, a little bit lost in his early 20s. He started college at Hope College, a small Protestant school in Michigan. After a couple of years, he decided that wasn't really for him, transferred to the University of Michigan. By his own admission, seems to have been kind of a mediocre student there, graduated, left academia for 4 years, but then came back and entered Princeton's chemistry program, got his PhD, and pretty much never looked back. His career really saw a meteoric rise after that. And to me, that just says that in higher education, we need to be open to people who take a little while to get started. There's this idea that one of the secrets of Silicon Valley's success is that it's a failure-tolerant culture, that you can found a startup, have it go bankrupt, and still have a chance to found another startup. And I think we need, in higher education, to maybe be open to the idea that something simpler needs to apply here, that there's some people who have trouble getting started in their 20s, but then end up contributing quite a bit. Lesson 2, be familiar with different types of organizations. Modern science is organizationally complex. On the left there, we have one of many, many organizational charts that were produced by the Manhattan Project. This is a project that had real difficulty figuring out how the different organizations involved were supposed to relate to each other. On the right, we have, again, one of many organizational charts produced by the the National Nanotechnology Initiative, an initiative that Rick Smalley played no small part in causing to be created. And as you can see, modern science requires different organizations to work together in very, very complicated ways. Smalley seems to have been a real master of that, of being able to move across organizational lines, of getting different organizations to work with each other, of playing roles in different types of organizations, in industry, in government, and obviously in academia. And I think to some extent, we can see that very early in his career. After he left Michigan, he went to work at Shell for 4 years. As he put it in his Nobel biography, quote, "These were fascinating days involving huge volumes of material, serious real-world problems with large financial consequences," right? He seems to really relish this work in industry, even though he then came back to academia for most of the rest of his career. He certainly never returned to the kinds of questions he was dealing with at Shell, though toward the end of his life he was interested again in problems of scale-up and manufacturing of large quantities of Bucky tubes, rather. But I think we can see in this ability to move among different types of organizations and to really relish different kinds of research, a real strength that he brought to his role at Rice. Certainly when he was at Rice, he was at pains at times to get the university to adopt some practices from industry. He was one of the driving forces behind the creation of our technology transfer office, and he also ran the equivalent of a pilot plant for manufacturing large enough quantities of Bucky tubes over in the Space Sciences building that they could be sold at cost to the international research community to develop new applications for fullerenes. So someone who, interested in helping different kinds of organizations learn from each other. All right, lesson 3, find the right partners. Rick Smalley came to Rice in 1976. 3 years later, in 1979, the Rice Quantum Institute was founded, and he became one of its founding members. Eventually, he became its director for 8 years in the late 80s and early 90s. RQI is by no means a uniquely Rice sort of institution, but I think it is the kind of interdisciplinary research unit that Rice has specialized in over its history. And you can see the reasoning behind that, right? We're a small school. It's very difficult for any of our departments to cover all of the things that the equivalent department at a large university like Michigan or Berkeley or MIT can cover. But if you can convene the right kind of interdisciplinary organization, if you can group together the right constellation of people from a bunch of different departments and have them tackle those kinds of problems that fall between disciplinary specialties, that can be incredibly effective. It doesn't always work. Certainly, the early Rice Quantum Institute had its share of personality conflicts, but it can work very well. And one of the most successful outcomes of the RQI early on was that it opened a space for Bob Curl and Rick Smalley in chemistry and Frank Tittle in electrical and computer engineering to recognize the complementarity of their expertise in a way that really contributed very strongly to the eventual discovery of the buckyball. And in particular, I'd note that of the 3 graduate students who were most central to the discovery of the buckyball, Jim Heath, Sean O'Brien, and Yuan Liu, all 3 worked with those 3 faculty members. And you can see here, Yuan Liu says, thank you to my 3 supervisors, Curl, Smalley, and Tittle. And that, in fact, was the thesis committee for Sean O'Brien, really. So, my point here is just a lesson from Smalley's career is that the right kind of institution that can foster the right kind of complementary partnership can really achieve great things. Okay, now we're really getting into the heart of the story of the discovery of C60. And one of the things that really leaps out at you almost immediately when you look at this story is just how odd some of the starting questions behind this research were. This discovery came out of a temporary partnership among Rick Smalley, Bob Curl, and an English astrochemist, Harry Kroto. Kroto had this idea that this apparatus that Rick Smalley had built could be used to simulate conditions in interstellar space, and that would then allow one to discover something about the composition of interstellar matter. It's interesting, too, I think, that after this initial discovery of C60, the second big discovery in the Buckminster-Fullerene research community was made by people who were following very similar questions. A team of astrophysicists who also were interested in learning about the interstellar medium discovered a way to make large enough quantities of C60 that the first reliable infrared spectroscopy could be done on this material, answering a lot of very open questions about it. Now, I don't think it's, I would say that the interstellar space is about as far from the marketplace or the clinic or the battlefield or any context of application that you can imagine, right? And yet, clearly, the research community that came out of talking about interstellar space has turned out to have relevance to those contexts of application. Now, I think Rice partisans would maybe to some extent minimize the importance of astrochemistry and astrophysics in the story of how C60 was discovered. But even there, I think it's important to note just how crucial it was that Curl and Smalley and Heath and O'Brien and Liu had the liberty to stop what they were doing, to look at this anomalous result, to ask, why is there this really curious peak at 60 carbon atoms, and then to reorient their research programs to take advantage of that anomaly, to pursue this intriguing question without having to constantly justify any sort of near-term application. That liberty to be driven by curiosity really made the discovery of C60 possible. But then the flip side of that is that as much as healthy research communities depend upon basic researchers, people driven by curiosity, they also depended upon people who are driven by specific problems or who are employed by industrial concerns. Once C60 was discovered, a research community slowly began to grow around it, a community that was populated both by people who were interested in answering these very basic questions about what this molecule was, but who also began to ask, what might it be good for? And certainly the original team encouraged some of that. They talked about maybe this could be used in high-tech lubricants, maybe it could be used as a drug delivery device. And that encouraged people from places like IBM and NEC to get into this business, to start learning how to make fullerenes, to characterize their properties, and to think about how to use them. And the next major discovery in the evolution of this research field was the discovery of single-walled carbon nanotubes, independently by researchers at NEC in Japan and at IBM on the West Coast, a discovery that in turn fed back very quickly into Rick Smalley's own research program and really convinced him that this was the material to which he should dedicate the rest of his career. Right? So my point here is that if we take the fullerene research community as an example of a healthy research community, we can see that it involved people from a whole mix of backgrounds and with a whole mix of orientations to when and if their work would find some kind of application. Maybe another way of putting that is that the outputs of research are very diverse and sometimes rather intangible. I'm an historian. Historians tend to tell stories and not worry too much about measuring things. But as an historian of science, my work certainly meets up with the work of economists and sociologists and management scholars and science policy experts and even university administrators who are very interested in measuring the outputs of scientific research and their contribution to economic growth, and in finding the right metrics for understanding how a healthy research community should operate. And I think there's a growing sense, I hope anyway, there's a growing sense in those communities that basing decisions on metrics that rely too much on just those things that can be counted easily, on just counting things like publications and patents, actually ends up hurting the scientific communities that you're trying to foster. And that's because scientific communities produce a whole lot more than publications and patents. They produce a whole lot of things that are very difficult to count or measure. If we just thought about what Rick Smalley's lab group was producing at the end of his career, and this is a picture from his website at the end of his life. If we tried to think of what his lab group was producing, we would find a lot of different things, right? I mean, publications and patents, for sure, but also students and personnel, prizes, the Nobel Prize and a bunch of others, and with those prizes, the cultural capital to make big institutional changes, both locally at Rice and nationally. We would find consulting for industry and advice to government agencies. We would find him giving public appearances, locally, nationally, and internationally, that inspired an interest in science in everyone from wealthy donors to working class school kids. We would find outputs like new centers and new faculty lines and shared equipment and even a new building here at Rice. We'd find a startup company, Carbon Nanotechnologies, Inc. We'd find administrative expertise in people who had passed through Smalley's group and who went on to run centers and startup companies and the like. We would find material outputs, right? He had this pilot plant that was making nanotubes and distributing them globally so that people could discover new applications for this material. We would find partnerships as a result of his work, some new, some reinvigorated, between Rice and organizations like NASA or the Welch Foundation. And we would find a whole set of partnerships within Rice's own departments, right? Et cetera, et cetera, et cetera. Whole bunch of outputs that are very hard to reduce to some set of numbers. All right. Well, if the outputs of science are diverse, the inputs are as well. One of the examples Kevin and I give in our technology disasters course is we look at Soviet engineering, and we show that one of the reasons Soviet engineering was prone to spectacular failure is that Soviet engineers were trained in a very, very narrowly technical way, right? That the Soviet engineering education system believed that they could instill everything engineers needed to know at the beginning, and they didn't need to learn anything more afterward, and they didn't need to look outside their specialties in order to deal with the situations they would face. Whereas it turns out that the world is complicated and unexpected, and scientists and engineers need to be pulling in a very wide range of cultural resources in order to deal with the unexpected, in order to be flexible in the face of change. And we could find lots of examples of that from Rick Smalley's career. This is just one, his ability to draw on cultural resources from futurism and from science fiction. These are both books that he read sometime in the early 90s. This one by Eric Drexler is a very far out futurist vision of what nanotechnology would do for the world. everything from space travel to immortality. And Rick Smalley, he clearly had a lot of problems with that vision and eventually became a very public critic of it. But he also took that book and he distributed it to Rice's trustees and to administrators here and said, look, this book has a lot of problems, but it's a very compelling vision for this new thing, nanotechnology. This shows that this way of doing science, this way of thinking about the ends of science, has a real persuasive power to it. We should go in that direction. We should build ourselves up as a preeminent nanotechnology school. The other is this book by Arthur C. Clarke about an elevator from the Earth to space. Again, a pretty far out concept, though maybe a little more plausible than some of the things Drexler talks about. But you can go to the archives and find some very touching correspondence between Rick Smalley and Arthur C. Clarke, both of them saying, you've inspired me, you've inspired me. And you can see that very clearly in this cover image for an article by Smalley where basically, what's being said here is, look, carbon nanotubes, that's the material that one would make a space elevator from, right? That this is a vision of the kind of furthest out possibility for this extraordinary material. OK, last one. So Smalley really loved this picture. It's on lots of the websites he created. And this is, I think, the kind of classic way we think about Rick Smalley as this great individual genius, this man of incredible charisma and ability to persuade. And I think, definitely Rice should be encouraging that kind of individual achievement and should be looking for the next Rick Smalley. But, in his own work, Rick Smalley also understood the importance of collective achievement, of building institutions that would allow a group of individuals to do much more than they ever could on their own. That institutions allow individuals to discover collaborators, to find resources, to share equipment and overhead, to acquire knowledge that they wouldn't have available to them. And that's why he built or molded a whole series of institutions here at Rice and then beyond Rice's borders. So definitely, while I think Rice should do everything it can to encourage individuals, it also should take a page from Rick Smalley's book and look to how we can build stronger institutions. OK, thanks.
All right. Thank you, Cyrus. So at this time, we're going to have Cyrus and Jim come join us at the panel. Some people are leaving, but this is where the good part's going to happen. And also on the panel, we have joining us Professor Ajayan, who joined Rice recently from Rensselaer Polytechnic Institute, but who has also worked in the field of carbon nanotechnology immensely. And I've had the pleasure of actually doing some nano-level quality control inspection on the graphene and other materials he's produced in his lab. Then, of course, we're still very lucky at Rice to have both Frank Tittle here, who's in the audience, and Bob Curl, who were involved in the research that allowed the creation of the apparatus that discovered the buckyball and allowed for basically the wonderful legacy that we've just heard about. So now we're going to open up the discussion for questions. All right, I see a few hands popping up. I had a couple ready just in case, but don't be shy. Fire away. And address them to a particular panelist if you like.
I have a question for Dr. So you mentioned the nanomotor. How do you transfer energy for it to move?
The motor, is this on?
Yeah. Yeah,
OK. So the motor, that particular motor absorbs a light. So a photon of light causes it to go from a twisted state to an orthogonal state, and it can relax back either way. But because it has a nearby stereogenic center, that's a chiral center, the two ways that it could go are diastereotopic, so they're naturally different in energy. And so it keeps going over the lower energy side, and it causes it to go unidirectionally upon impacting with light. The light happens to be ultraviolet. Yeah, for that particular motor, but that's inconsequential. That could be changed, but for that motor, it's ultraviolet.
So instead of exciting
I don't want to get too much into the chemistry details. I think you can track Jim down and talk with him about the specifics of that motor later. Other questions for the panelists regarding carbon nanotechnology? I have one for Bob Curl, and I have a really good opportunity to ask it since I have him in a confined space. He can't get away. One of the interesting things about a lot of new discoveries in new technology, whether it's the discovery of the buckyball or the invention of the scanning tunneling microscope or discovery of high-temperature superconductors, whenever you come across something very new and revolutionary, you basically run into a lot of friction. Bose-Einstein condensation, another famous discovery that Rice was part of here. It was also a part of Rice's history happened. And my question for Bob is, you had years where there were a lot of questions raised about was, it really this beautiful soccer ball molecule, and sort of how did you get through those days and nights, and what advice do you have for researchers?
Well, it really wasn't very hard. I mean, I essentially was convinced from the first time I saw the C60 structure that it had to be right. The issue that was sort of overwhelming was the idea that all of the other even-numbered peaks that we saw in the peaks with even numbers of carbon atoms that we saw in the mass spectrum were also carbon cage compounds. So we had a whole new class of molecules called the fullerenes, and that I found such a mind-boggling thing that I was not quite sure about that. But we were savage. There was a paper called C60 lanthanum, a deflated soccer ball, and then there was an article in the CNE News in which some of the people in the soot community compared us unfavorably with cold fusion.
The pitfalls of being a scientist. Other questions for our panelists? Yeah.
Do you see any trends toward or away from your research as applied?
Who are you addressing that? Who would you like to tackle it first?
I'd like to respond because I certainly do. It's an interesting question. I mean, there are basically two kinds of research: those that are driven entirely because you're curious about something, and those that are intended to result in some practical application. And a lot of very eminent scientists have been involved in both kinds of things. It's not at all uncommon. Probably the Pasteur is the most strongest example of that. But I think I think going to the extreme of only being interested in applications and not satisfying your curiosity ultimately is not rewarding. But my colleagues may have a different impression.
I think Professor Ajayan's going to add to that.
Yeah. Well, if you look at something like carbon, carbon has been around for a long time, and the applications of carbon are really varied. If you go many decades before, you'll find graphite, which was used in nuclear reactors. Then came the carbon fibers, the intercalated carbons, and the last 2 or 3 decades have been nanocarbon time. And to me, I think what is interesting is that we applications aside at this point, what we have done is we have learned much more about how the basic carbon can be engineered. Of course, apart from all these graphitic structures, there's also diamond, which is another type of carbon. And many of these carbons that have been really practically useful, like activated carbon or carbon black or things like that, have this mixture of bonding of sp2 and sp3 hybridization. So what I think is that with all this learning that we have had over the last many years or decades, we might be able to engineer exactly the right kind of carbon that we want for applications. So I think this is the accumulation of knowledge that might lead to the next generation of carbons in the future.
Okay. Yeah.
Do you see this field expanding any other elements like boron nitride or silicon?
Yeah, absolutely. Well, silicon has enjoyed a special place already. But boron nitride, certainly things are moving into that, and there's molybdenum sulfide, there's all these 2D materials coming out on these sheets as well. And boron nitride is really special because when you put graphene on top of boron nitride, you don't get any traps, and it really shows tremendous electronic properties. So even the structures are piquing people's curiosity to move into the other elements that might do the same sort of thing. So this 2D sheet structure, for example, is not unique to graphene.
Do you want to add to that? I know,
Yeah,
I know Professor Ajayan works on boron nitride too. So.
Well, I think basically all these layered structures or one-dimensional structures, whether it is based on carbon or other layered material, what ultimately the goal is to be able to really engineer these things. I mean, we have, for example, a couple of big programs starting where the idea is to create three-dimensional structures. You know, if you look at the famous picture that was shown from the American scientists talking about this elevator to space, I think it's a beautiful concept. I think the problem is we don't know how to engineer this macro-scale structures from the building blocks that are nanotubes, right? So I think all this learning that has happened might help us ultimately to build that structure, you know, a macro-scale structure that would be practically useful. I think that's where we are today.
Okay, we have a question back there.
As part of the original discovery in 1985, I've heard two things that I wanted to ask if they're true. First, that when you first saw C60, you worried the machine wasn't working right, and you had to check that out. And secondly, that a mathematician was called as you tried to figure out what the structure was like.
Well, I don't recall ever being worried about whether the machine was working properly. That didn't seem to be an issue. We did call a mathematician. This is one of my favorite stories. Many of you have already heard this. We call Rick. We had this paper object that Rick had constructed, and you look at it, and it was pretty crummy looking. But so you couldn't figure out what he really had. So Rick called the chairman of the math department, Bill Veach, at the time, and asked him, you know, what he had. He had to describe it. It had 60 vertices, 20 hexagonal faces, 12 pentagonal faces. What do we have here? And so Veach said, I'll have to think about it. I'll call you back. And in about less than 5 minutes, he called back. And I'll swear I was the one that answered the phone because I remember this moment so clearly. Veach says, what you have there is a soccer ball. And it's very hard to come up with something to say after that. I finally asked him, what it was, what mathematicians called it, and he said it's a truncated icosahedron, and it's not new. Later, I found out that it was one of the Archimedean solids.
All right. We have a question in the back there. Cyrus, you want to start off on that one? Oh, okay. Jim, the risks and concerns?
I think there are certainly risks, and people need to try to mitigate the risks. I will tell you that some of the cries that there have been really unreasonable. For example, if you were to happen to find a toxic organic compound, would you cry for the immediate moratorium on the research on all organic chemicals and research? And so within nano, you're going to find toxic substances that may enter the body in different ways, and these need to be studied. And each material is different and needs to be evaluated in its own right. So to say, I have a toxic nanoparticle, therefore all nanoparticles are bad, is not true at all. And so, and as soon as you change the surface charge, you change the surface bonding groups, you change the size, you change the shape, the properties need to be examined. But we know how to do this. This is called, you do an MSDS, you do a report on a particular compound. It's done in organic chemistry all the time. So each new compound has to be examined and to studied for its environmental fate, for its biological fate. It has to be taken seriously, but there are mechanisms to do that.
Okay. Yeah.
So
a lot of the debate about the ethics of nanotechnology has centered on these questions about toxicity, which I agree are, for the most part, often overblown. What I would add to that, though, is that, I mean, to me, nanotechnology has a number of applications, but it is also an innovation in the organization of science. It's a new way of creating new kinds of interdisciplinary collaborations and new sorts of institutions. And institutional change is great, but it's also not something that should be done unreflectively. So to me, an ethics of nanotechnology might want to take account of these kind of questions about toxicity, but it should also take account, do we know what we're doing as we're changing the conduct of science? And questions like this one about, the mix of basic and applied, I think, should definitely be part of, any ethics of nanotechnology.
Okay. More questions? Yeah. Oh, I guess that's just for you, Jim. He asked about basically the stability and about the nanocars. How stable are the nanocars? How maneuverable are the nanocars?
The nanocars are stable to about 200 degrees centigrade, and then they start decomposing. When you have the fullerene wheel, it breaks at the axle at about that temperature.
Yeah, we have a question.
Is it just the wheels that come out of the carbon nano, technology here, or is there other aspects of the guts of the car?
Right. So the question is what more of the car is nano besides just the wheel? I mean, the whole car is nano. To think of it in terms of doing work with a single molecule and observing a single molecule, that's all nano. You need nanoscopic tools to do that. And until recently, there weren't good tools to be able to watch any of those. In fact, that's the slowest step in the research. It's on Kevin's side. It's imaging
My
these
fault.
structures. We can actually make them much faster because we have 150 years of organic chemistry, 75 years by design that help us to build these structures. But it's learning how to manipulate them that's all part of nanotechnology.
Okay.
I thought I heard him say something, was it all carbon, or was it all?
It's almost all carbon. There's a few hydrogen and nitrogen fuel. It depends on the structure and the functionality that Jim wants to build into it. I wanted to sort of build on that idea, and I think one of the really interesting tensions that came out of the nanotechnology thrust in the 90s was between Smalley and Drexler, and how basically I'm very curious to get Jim's opinion on, and Pulickel's, on their relationship between how far they think we've come and sort of distinguish what we can do with nano now, because a lot of it to the layman's eyes looks like, oh, we are doing what Drexler said, so he was right all along. Can you sort of both speak to about how what we're really doing is different and similar?
Yeah, we're not doing quite what Drexel said that we would do, and even the way that I paint the nanocars of ultimately what we'd like to do is bottom-up construction. There's a lot of unknowns in that and a lot of very big hurdles to be able to do that. It's very easy to say that we're going to mimic enzymes. What enzymes do in vivo, we're going to mimic ex vivo by doing assembly, but we can take care of that in some manner and lower the barriers by saying, well, we're going to make something very small, like a 50-atom quantum dot memory. Then all we've got to do is have cars bring up 50 metal atoms all together, put an electron in there. That's a quantum dot memory. It's a 1-bit quantum dot memory, but it is bottom-up construction. So you can choose easy targets, but it's going to be a long time before we can release the nanocars and build buildings like this. But one day that will come, I think.
Professor Ajayan, would you like to build on that?
Well, I mean, rather than repeating what Jim said, let me add my perspective to nanotechnology. I always like to talk about the intrinsic challenges and the limitations of nanotechnology. It's very simple. You're basically building materials that have a few 100 atoms, a few 10 atoms. And the problem is that with a small change in the number of atoms or the morphology that you create, you have pretty dramatic change in the behavior. So nanotube is a good example. You have a small variation in chirality, and you go from metallic to semiconducting. Now, from a person who is synthesizing this, the issue is how controllably you can do this. So, I mean, both from the perspective of nano manufacturing as well as this bottom-up assembly of materials, you have this disconnect between what you can do from a synthetic point of view and what is actually expected and what is the result of these kind of manufacturing.
Okay.
So I think there is this disconnect that I would like to bring.
And I had a comment about Drexler. Drexler's book essentially was saying that you could build very tiny machines, nano or micro machines, that would be able to build other machines and self-replicate, so that you would be creating a new mechanical species. And of course, this was put in this book called Prey, where they got out of the lab and attacked and were wiping out humanity. And Rick had a big quarrel with that because he felt that this clearly was going to violate the second law of thermodynamics.
I think Cyrus used that as a textbook in the class for a while of the nanotechnology content and context, so he might also want to make a comment or two on Drexler versus Smalley.
Well, I mean, what I would just say about Prey is you'll notice it's one of a vanishingly small number of Michael Crichton books that hasn't been made into a movie. So I think some of the fears that this would, cause some sort of revolt against nanotechnology have been very overblown. It had a much lower sales than most of his other books.
Okay, and we have another question?
To anybody on the panel, is there any interaction between holography and nanotechnology at this point? Calling your attention especially to the vibratory world as opposed to the particular world.
So I'm as qualified as any, which makes me slightly more qualified than other people. I would say that the nano world deals very specifically with materials, right? And these materials can benefit lots of different fields. And I think that, one of the interesting things that always happens in your research is, are you doing evolutionary work or revolutionary work with those materials? But in the different fields, there's also other things that limit how well nano can be applied in those fields. So, I mean, I don't want to speak specifically because I don't do exactly research in that, but I mean, nano is everywhere now. And in fact, one of the real interesting questions to ask is, a lot of this came out of the NNI from the National Science Foundation. There's a question of, should that continue? And should specific nanotechnology journals continue, or will it become just sort of part and parcel of every field of science and engineering? So, I think it's touched on a lot of different areas: biotechnology, information technology, but there are fundamental physical limits in these other stuff. Yeah?
Right now, we're kind of in a time where chemistry and material science and physics are all kind of blended together. What sort of curriculum do you guys suggest for students who are interested in this sort of stuff? And how do you think that your personal background has influenced what you research?
So I think it's important to be a good chemist or physicist or material scientist, because people who try to sell themselves as nanotechnologists don't get good jobs. And so it's important to be really good in a particular area. It's certainly, I mean, you can see synthetic organic chemistry in everything I do, and the training, whereas in some of the other folks on this panel, it would be different. It would be based on their particular training. So I think that what you want to do is you still want to get a degree in something traditional while working in an area related to nanotechnology.
I'm always in favor of removing boundaries and having just pure sciences versus applied sciences. But I may not win against the administration. So, but I think that this is going to be more and more happening. At least in research groups, this is happening. You have people from all kinds of fields, and we continuously think about what kind of curriculum would fit these kind of disciplines.
I'll just add my 2 cents, which is, get a solid fundamental foundation in any of the science and engineering fields, and then from there you can build up. But I do think that it's also very interesting. Typically in natural sciences, you always have physics, chemistry, biology, and it's the schools of engineering where you do see the new departments pop up and last for a while, and they might not stick around. I always joke, we don't have a department of buggy whips in engineering here at Rice, but it's that type of idea. So that's where you see the new ones ones created, like bioengineering is one of those fields. However, I still feel, being an electrical engineer, that maybe bioengineering undergraduate degree is useful, but it's very specific, whereas electrical engineers or mechanical engineers or chemists and physicists can go into bioengineering later with the same fundamentals. So, other questions? Yeah?
Targeted tumor, and how were you able to penetrate the cell?
The carbon nanoparticle targeted the tumor by having a monoclonal antibody attached or physisorb to it. So that targets the cell surface. The way the drug gets in can be either diffusion of the nanoparticle in carrying it or just having a high local concentration of the drug surrounding the cell.
Okay, thanks. I want to ask one more question again now that I have Cyrus pinned up here. Basically, the role of government in this fundamental research, and all of you and myself are participants in it. I pay in taxes to this pork, which it literally is. I mean, it's good pork versus maybe bad pork, and that's an interesting debate to have. But one of the interesting things, and one of the things that Rick Smalley was fundamentally involved with was the National Nanotechnology Initiative. And so I want to ask Cyrus sort of how he sees that playing out. Was it an overall good, or was it overall evil, or is it sort of neutral? And then should there be another one, or should it has it run its course?
I certainly wouldn't call it an evil. Yeah, well, I mean, I would definitely be interested to hear what the rest of the panel has to say about this. But from where I sit, I mean, the NNI has been an interesting experiment in interagency cooperation and in having some coordination across many agencies in how those agencies foster a particular set of research areas, and in guiding those agencies to fund particular kinds of research and to look into particular research areas in their own labs and to create particular kinds of institutions, academic centers, and so forth. And so, that kind of experimentation in how governments relate to scientific communities, I think that should be encouraged, but I think, we should also be willing to pull the plug if the experiment doesn't work. And I'm sure that will eventually happen with the NNI. It won't run forever, and something else will come down the pike, which hopefully will learn some kind of lesson, hopefully learn historically informed lessons from how the NNI operated.
Okay. Professor Curl?
Well, one of the things about Rick was that he really pursued, at least in his early career, he really pursued particular ideas for a relatively short period of time. He was a tremendous instrument builder, and he would dream up an experiment that would give you some sort of new information if you just built a very big, complicated instrument to carry out the research. And he would build these instruments incredibly short period of time from concept to finish, and he would then a year or two later build a new instrument usually for a new purpose. And what happened with the National Nanotechnology Initiative, I think that Rick realized that there was an opportunity in terms of new instrumentation that he hadn't developed, but which was important. Science has always gone in the following path. It's always the invention of a new way of observing things, followed by a period of observation, which often led to a new idea for a new instrument to observe things with. And the particular things that I think Rick was thinking about in particular were the development of the proximate probe microscopes, scanning tunneling microscopy, atomic force spectroscopy, etc., which combined with tremendous advances in electron microscopy made it possible to actually see what was going on, at least on a surface, in more detail than had ever been possible before. And this was the fruition, really, of the idea of Richard Feynman, who said that in the 50s that all the physicists should get busy and build instrumentation or design instrumentation for looking at nanoscale species. And so I think he saw an opportunity that could be exploited by science. Knowing Rick, I don't think he would like to see the National Nanotechnology Initiative go for a whole lot longer, even though he did spend the last 13 years of his life on one particular project.
All right. Yeah.
Well, I think it's important to have this academic industry government nexus. I think it's it allows, especially if there is a new field, to foster it, to take innovations and make it into practically useful areas. I think Japan is a very good example where this nexus is very strong. And I think perhaps NNIN served its purpose, and now the technology has become mainstream, so it gets distributed into everything else.
Okay. Okay. All right. Well, I think now is the time to thank our speakers and the panelists for a wonderful, entertaining hour and a half.
This program is protected by a copyright and may not be redistributed in whole or in part without the express written consent of Rice Digital Media Services.